Today we have a quick lesson to explain the most commonly occurring shapes in frequency distributions. The shape of a distribution is described by its symmetry and number of peaks. So if we're looking at a graph for a frequency distribution, we're going to look at the symmetry of the graph and the number of peaks that the graph exhibits to identify the shape of the graph. So in this lesson, we're going to discuss the 5 most common or frequently occurring shapes that occur in frequency distributions. The first shape we're going to look at is bell-shaped or symmetric data. The graph is exactly as it sounds. It exhibits a bell shape. We have a single peak. And if we had to split the graph down the middle, so down through that peak, we would notice that it seems as if the graph almost has a mirror image on either side, and that's what we refer to as being symmetric. Okay, so let's look at an example. Let us assume that we were interested in the heights of a group of males. So on our x-axis, we have the various heights measured in meters, and on our y-axis, we of course have our frequencies. So essentially what this graph is telling us is how many people or how many males have a specific height specified by the height on the x-axis. So let's interpret this graph. We can see that the most number of males, that's about 40 males, have a height of 1.7 meters. And then we notice that from that point, if we have to go back, so moving from 1.7 and going down towards 1.3, we notice that the number of males start to drop. And if we had to go forward from the point of 1.7, so from our peak, we would notice that the number of males drop again. And it almost has a symmetric shape to it, suggesting to us that the bulk of males have a height of 1.7 meters or around 1.7 meters, and only a handful of males are considered to be on the shorter side of the scale and the very, very tall side of the scale. So they have heights amongst 1.3, 1.5, 1.9, and 2.1 meters. The next shape that we're going to discuss is the uniform or rectangular shape. And as you can probably tell, the names really depict what the graph shows us. So we're looking at a graph that essentially has no peaks and it's basically rectangular in shape. So we just have this straight line that's forming going across. Now let us assume that we were interested in the quantities of t-shirt sizes sold. So I don't want you to think too much about this. Don't try to put this in a realistic sense and confuse yourself. Just take it for what it is. I'm just using made-up examples to explain this in the simplest way. Okay, so on our x-axis, we have the various sizes from size super small to size extra large. On our y-axis, we have our frequencies. So this graph is telling us the quantity of t-shirts sold per size. And we can see that every size seems to have sold the same amount. If you want to think of this realistically, or if you just want to wrap your head around it, then maybe you can just assume that we stocked up 30 units of each size and we happen to sell out of every size. So that's probably why we have the same amount of sales or same amount of units sold per size. Okay, moving on to bimodal shaped data. Bimodal suggests that we're looking at 2 modes, and that's exactly what's happening. We're looking for 2 distinct peaks occurring in the graph. As an example, let us assume that we're interested in the number of customers in a restaurant at given hours. So on our x-axis, we have times 9 a.m. to 9 p.m. So essentially, we're observing this restaurant for a 12-hour period. And then on our y-axis, we have our frequency. So this graph is telling us how many people are in the restaurant at the given point in time on our x-axis. So interpreting this graph, we see that we have 2 distinct peaks at 12 p.m. and 6 p.m. At 12 p.m., we have 25 customers in the restaurant, and at 6 p.m., we have 30 customers in the restaurant. And between those times, we see that there's a dip in the number of customers. So at 3 p.m., we only have 10 customers. And then at 9 a.m. and 9 p.m., we seem to have little to no customers. Okay, so moving on to our second last shape, we're going to look at positively skewed data. So essentially what's happening here is I want you to think of the bell shape. And if you had to grab onto the right-hand side of that bell shape and pull it to the right, you would end up with positively skewed data. So what that's suggesting is that we have data points that are essentially causing the data set to skew to the right. And we refer to those data points as outliers. So in our data set, we have maybe, let's, as an example, say that we have 5 data points, right? So we have the values 10, 20, 30, and then we have the values 150 and 200. So that's an example of having outliers. The values 150 and 200 are relatively large in comparison to the rest of the data values. So that's just a really simple example to understand how extreme values can cause your data set to skew. Let's look at this example. So we're interested in the mileage on a group of used cars for sale. So on our x-axis, we have the mileage measured in kilometers. On our y-axis, we have the frequency. And this graph is telling us how many cars have the specified mileage that is given on the x-axis. So interpreting this graph, we see that there's about a handful of cars that have a mileage of 20,000, somewhere between 0 to 10. And then we have approximately 50 cars with a mileage of 40,000 kilometers. And from that point onwards, we notice that now we start to drop. As the mileage is increasing, we notice that the number of cars are dropping. And this is suggesting to us that whilst most of the cars in this data set have a low mileage, there is a handful of cars in comparison that have a really high mileage, and that's causing the data or the shape of the data to skew. And you probably already guessed this. If we have positively skewed shaped data, then we definitely have negatively skewed shaped data. So this will be the last shape that we look at, and we're going to look at the example where we're interested in the number of ice creams sold per day for a given week. So on our x-axis, we have the days of the week ranging from Monday to Sunday. On our y-axis, we have the frequency, so the number of ice creams sold. And essentially, this graph is telling us the number of ice cream sold per given day in a given week. Now, if we look at this graph, it is very, very clear that the graph is being pulled to the left. It looks skewed to the left. And why is this occurring? And that's probably because if we look at Monday to Wednesday, we notice that there is a very low number of ice creams being sold. So that suggests to us that this is where the extreme values are. These are outliers in comparison to the rest of the data set, where we notice we have about 25 ice creams being sold on Thursday, about 50 ice creams being sold on Friday, and about 40 ice creams being sold on Saturday. So because of those extreme values occurring at the beginning of the week, it's causing the data set to skew to the left. That brings us to the end of the lesson. Thank you so much for watching. If this video has helped you in any way, kindly like and subscribe and turn on that notification bell to keep learning.